just going to quickly review what we did last time and then continue. Any questions before I get started? Everybody's happy? Okay, so we're just going to finish up our review of probability today and then start probability inequalities. Remember the things that we reviewed on Monday's class: sample space, random variables, CDF, expected values, and then talk about transformations of random variables. So we're at page 4 of the first set of notes. The top of page 4 points out that we can also do change of variables for sets of random variables. So for example, I might have a pair of random variables xy with some function g of xy, like x divided by y or x minus y, and the same principle applies. So if there's a homework problem about this, and if you've forgotten how to do this, just remember it's always the same principle. You just say, well, what would the CDF and the Z be? And that's just by definition the probability. Z is less than the Z, that's just definition. And plug in what Z is, probability G of xy is less than Z. Little z, remember, is just a real number. And now this is some event about the original random variables x and y. So this is the double integral, in this case, over the set A, let's call it, of pxy. And it might take some thinking to figure out what this event AZ is. The AZ are the set of all pairs x and y would satisfy this constraint. So you just have to think through. In the homework problem, you want to draw a picture of the sample space and what this constraint looks like, and then you can't go wrong if you do the CDF. And then, of course, once you have the CDF, you differentiate to get the PDF. So if you've forgotten how to do that, that's a good thing to practice, because there will, remember, be the test next week on all this review material. So I want to make sure that I do this kind of problems. Okay, so we mentioned independence informally several times. In the first lecture, let's remind ourselves what independence actually is. So two random variables x and y are independent. And the way I'll write that in this class, not everybody uses the same notation, but that's going to mean x is independent of y. So intuitively, that means physically, if you think of generating random numbers, that the random number generator for y is not affected in any way physically by the random number generator for x and vice versa. But the way we express that probabilistically is that the joint probability statement about x and y, so the probability that x is in A and y is in B, is always equal to the product, the probability that x is in A. And this has to be for all events A and B. So that's either a physical fact about whatever situation you're studying, or it might be an assumption we're making. We might start off and say, let's assume that x and y are independent. If we do that, though, always keep in mind it's an assumption. It may or may not be true. And of course, a lot of statistics in machine learning does take independence of random variables as an assumption, so that's something we have to be careful of. How would we check this, though? How could we ever possibly check this for all events A and B? What do you actually do? Say on a test. Find out if x and y are independent. Densities or distributions, right. So you know that an equivalent thing is that the density for x and y, or the probability function, factors, and let's keep track here though, that this is the density. This is the density function for the pair x, y. This is the density function for x, and this is the density function for y. And this has to be true for all x and y. So that's usually much easier to check. And when we talk about a set of random variables, let's say n random variables, of course, independence means that the probability that x is in A1, x is in AN, again, is equal to the product. That's what we mean by saying that these are mutually independent. So if I draw a random sample of people and measure things on them, which is a common situation, and one person doesn't affect the other person's outcome, then they would be independent random variables. And again, we typically would be looking for, this would now be a multivariate distribution for n-random variables. And for independence, we'd be looking for that being equal to the product not only are they independent, but they're drawn from the same distribution. So we have n observations, they're independent observations, they're each drawn from the same population, or in other words, they each have the same marginal distribution. So remember what the terminology is. We usually call that IID, which stands for independent and identically distributed, right? They all have the same marginal distribution. So if they all, this is independent, identically distributed. They all are drawn from the same distribution. Intuitively, this means a random sample population. And that's a lot of data that we deal with, or at least approximately of that form, and most of the things we would have learned in identity statistics, machine learning is in the IID framework. So we have n observations drawn independently, identically distributed, and so the symbol we'll use for that is x1 to xn, and then twiddle p. That's short form for, whenever you see that, they're independent and identically distributed, and they're drawn from a common distribution p. So keep in mind, this is an assumption. Right, a lot of stuff we learn, we're going to mostly concentrate on the IID case because that's the easiest case, and we can't do more complicated cases until we can do the simple case. So we usually start with the IID case, but it doesn't have to be true. If you assume things are IID or not, the method we derive won't be valid. We also write this sometimes, so sometimes I'll write it like this, that's the probability distribution. Sometimes I'll write it in terms of the density function. And this is just saying that drawn from this density, it's just whichever one is convenient. Sometimes we express it in terms of the CDF. And these are all equivalent. It's just different notation for the same thing. CDF version, PDF version, distribution version. And the question is, when should you assume it's IID and not IID? And for this class, if I don't say, then the default is it's IID. If it's not IID, I'll tell you. If I don't tell you, you can assume it's IID. Okay? All right, so we have whole classes devoted to what happens when it's not IID. So for example, if you have data like stock data collected over time, they're going to be correlated over time. They're not going to be independent. That's called time series data. So we have a whole class devoted to time series and stuff. So departing from the IID assumption is quite important, but we're going to mostly start staying there. All right. Any questions? Good. All right. The next section of the notes is really for reference. It's in the book, it's in the notes. I won't go through it in much detail, but it's just a reminder of special distributions. So in general, a probability distribution is just some distribution P. But there are, of course, special distributions that we use a lot. So this is just to remind you of what some of these distributions are. Again, this should all be reviewed. So for example, the normal distribution looks like this. X is normal mu, sigma squared. What does that mean? Well, remember, it means that there's a probability density that looks like a bell-shaped curve. The center is mu, sigma controls how spread it is. What's PDF? PDF looks like this. And you'll remember that there's all kinds of special properties of the normal distribution. This is a good point, though, a good time to make an important notational point, which is the difference between random variables and parameters. So the normal distribution is a little bit of a misnomer. It's not a distribution. It's a family of distributions indexed by two parameters, the mean and the variance. So I should really write it like this. So So what this means is the random variable, the random thing we're drawing is x. That's what this is a probability density function for. This is x. But the distribution has these two free parameters in it. In this case, the mean and the variance, mu and sigma. So I'll always do this, or most of the time I'll remember to do this in this class. The random variable will be on the left of the semicolon. These are parameters. These are just unknown constants. They're not fluctuating. There's nothing random about them. They're fixed but unknown. Well, typically they're unknown. And so these are the parameters, and this is the random variable. The probability statement is about x. So it's really a family of distributions when we talk about a normal distribution. And sometimes I'll write this, another way to write this might be p sub sigma of x, whichever way is convenient. Just don't confuse the parameter with the random variable. Of course, in this case, there's two parameters. And we know that, in this case, the mean of x is mu, the variance of x is sigma squared. There's all kinds of other properties. Another important distribution is the multivariate normal, which some of you will have seen, some of you may not have seen. So let me just say what that is. So for the multivariate normal, we're actually no longer dealing with random variables. These are actually random vectors. So maybe I should go like this. In other words, each guy, say xi, is actually a vector. Xi, I'll try to like this one. Xi of what did I use for dimension here? So these are random vectors. What's a random vector? It's just a vector where each element of the vector is a random variable. And so this is in R to the D. And the multivariate normal is just like the normal, except, you know, if I think of my table here is like a two-dimensional sample space, and now I have like this bell-shaped function over here. So it's a multivariate version of the normal. And the probability density function is like this. But there's this thing, capital sigma. I think I'm missing, I think there's a typo here. So let's see what you recall. This should be it. Top of page 5. So what's this all mean? The only thing that's changed is, well, first of all, what is the mean of a random variable? What is mu? Mu is the mean of x. That's just the vector. So this is the mean of this. This second one is the mean of this, and so on. And similarly, sigma is now taking the place of the variance. It's the variance-covariance matrix. So this will be the variance of the first coordinate. This will be the covariance of x1 and x2. And so on. So it's a d by d matrix. Keeps track of the variances of all the random all the coordinates of the random variable, random vector, I should say, and all their covariances. So it's just the matrix version. And then this is the determinant of that matrix, and this is the inverse of that matrix. So we're going to use the multivariate normal quite a bit, and it's just we haven't seen it before, it's the multivariate generalization of the univariate normal. And a lot of properties, there's a theorem, well actually, the top of page 6, if you haven't seen the multivariate normal before, then later on you should look at the top of page 6 where I summarize the main properties you should know about a multivariate normal. The most important two properties are that the marginal distribution of any coordinate, or set of coordinates, is also normal, and the conditional distribution of any set of coordinates given the other set of coordinates is also normal. It's kind of not surprising because everything about normals is always nice, and so this is the multivariate normal has a lot of nice properties. So the normals are going to get used a lot. Another distribution that comes up a lot is statistics, and I've got to find the chalk brush somewhere, or we're going to have a challenge here. All right. I have to start writing smaller and smaller and smaller. I didn't find the rush. Suppose I have now, back to univariate, x1 to x, use the same notation I have here. Oh, sorry, let's say, call them z. z1 to zp. So again, this means they're ID, they're independent, same distribution. And in this case, they're normal, and they're standard normal, which remember means that the mean is 0 and the variance is 1. So these are just p draws from my normal. What happens if I take the sum of these guys, let's call it x, and square them. I square them up and sum them. That's a new random variable, and it comes up so often we give it a name. So what's that distribution called? Chi-squared distribution. But again, the chi-squared, you know this way, is not a distribution. It's a family of distributions. And it's indexed by a parameter. And the parameter gets the name degrees of freedom. And so this is called a chi-squared with p degrees of freedom. But just think of the p as just indexing which guy in the family it is. There's a whole family of chi-squareds. And this is the chi-squared with p degrees of freedom. This has mean p invariance 2p. That's a good test question. Show that the chi-squared has mean p and invariance 2p. So chi-squareds come up quite a bit. Few discrete, these are continuous distributions that we use a lot. Then there's our discrete distributions that come up quite a bit. So the simplest would be coin flipping or Bernoulli. So the notation will be that x is a Bernoulli. And again, there's a parameter. Right here. So that just means it's a coin flip. So x can either be 0 or 1. So the probability x is 1 is theta. Probability. And the probability function, again, x is random, theta is a parameter, can be written in the convenient form e of theta to the x. When x is 1, this becomes theta, and when x is 0, this becomes 1. What's another one? So another one that comes up is binomial. This has two parameters, n and theta. And we think of this as you flip a coin n times, to count the number of heads. Or in other words, it's the sum of n Bernoullis. And so the number of heads can take values from 0, 1, 2, 3, up to n. And you'll recall that probability function is n to the x. Theta to the x minus theta. All right, now there's a few other distributions here that you can look at and remind yourself: the Poisson, the uniform distribution, the multinomial, the exponential again. I'm not going to go through them all. You can, again, you'll have seen these before, but if you've forgotten, just look through the notes and remind yourself. I just want to make sure that if I ever mention them in class, you remember what they are, or if you don't, just go back and look it up here in the book. All right. So those are just common distributions that come up for various reasons. The next and last topic here on our review is the idea of sampling distributions in statistics. So it's very often the case that we have a sample and then we compute some function of the sample. defines a new random variable. All right, so we'll have x1 to xn, let's say it's IID, from some distribution P, some arbitrary distribution P. And often we, do something to summarize the data, or we use some function of the data. The two very common ones are sample mean, x bar. Now, a lot of times when I compute a statistic like this, and the statistic just means any function of the data, sometimes I'll write sub n, and that's just to remind you that it's computed from a sample size n. And keep in mind that this is really just some transformation. This is just some function of x1 to xn. So since x1 to xn are random, x bar is also random. If I drew n observations to compute x bar, and if I repeat that over and over, I'll get a different x bar every time, and it'll have a distribution. So this statistic, or this quantity, is a random variable. It has a distribution, and we call that the sampling distribution. It just means the distribution of this quantity. So what is the sampling distribution? It's just the probability that x bar is less than 15. In general, figuring out what this distribution is not easy. When you're going to do a homework problem, you just take the sum or difference of two random variables. So it's already can be difficult. Figuring out the average again can be pretty complicated. To make matters worse, if we don't know much about this original distribution P, that makes things even harder. But it does have a distribution, and this distribution has certain properties. And let's suppose the individual random variables each have mean mu, let's say invariant sigma squared. Then what is the mean of x bar as a random variable? Mu. It's also mu. So each individual random variable is mean mu. X bar also mu. So if I simulated n random variables, compute x bar, do that many times, and look at the average, it's going to be mu again, the same as the mean of the original population. But what's the variance of x bar? Sigma squared over n. So what that says is if the distribution of an individual xi, so in other words, the xi's are drawn from some distribution, say like this, it has some mean and some spread. If you now did a simulation, draw n observations, compute x bar, and repeat, that's going to have its own distribution. It's also going to be sensitive to mu, or have mean mu, but its variance is much smaller, so it's going to have a distribution that's more concentrated. That's the difference between the distribution of the x's and the distribution of x bar. Now there's another statistic, of course, the sample variance. There's a little bit of confusion here, which is some people, let's write it actually this way first. It's x r minus x bar squared, and we average it when we divide by n minus 1 instead of n. Why do people divide by n minus 1 instead of n? What nice property does it have by dividing by n minus 1 instead of n? Thanks. It's just convenient that it now has mean. However, there's lots of times in this class where you'll see I divide by n instead of n minus 1 for other reasons. And it really doesn't matter. If dividing by n and n minus 1 gives you much of a different answer, you've got way too little data. The difference between n minus 1 and n shouldn't be of any importance. But I'll try to be clear about which definition I'm using. I'll try to be consistent with it. There's lots of other statistics we can compute from the data. As well, of course, we compute the median of the x's, we compute the maximum, the minimum, and so on. So there's lots of them. The mean and the variance deserve special mention because they so often. These properties that I just wrote down don't depend at all on what P is, except we're only assuming that the data are IID and that the mean and the variance exist. In the special case when the original distribution was normal, we can say a little bit more. If x1 to xn are not just only IID, but they come from a normal distribution, well then of course these properties that I mentioned here still hold. But we can say even more. X bar itself has a normal distribution. How would we prove that, by the way? We would prove it by computing the moment generating function of x bar. It's very easy to compute it. And because a moment generating function completely characterizes the distribution, you compute the moment generating function and you see, oh, this is the moment generating function for a normal with mean univariate sigma squared over n. You're done. And that tells us that x bar has a normal distribution. And the sample variance divided by sigma squared has a chi-squared distribution of n minus 1 degrees of freedom. And in fact, x bar is independent of the sample. But these properties here are not general properties. They only hold if the original data are normal. These properties are general properties. Okay, so we've done a very fast review of all the stuff you should remember in probability theory that we're going to need to go forward. And so now we're going to start pressing forward. But let me just check and see if there's any questions about anything. No questions. Yes?
So the material on the upcoming exam will go up to this?
Yes, this would all be familiar for the test.
One question. The joint probability is the probability of the intersections of events, or like how does this set theory apply?
So the joint distribution the way to think about the joint distribution is, let's say I have a pair of random variables. It's about actually arbitrary events in the whole joint space. So I'm going to have a density function, which is a function of two variables. It's non-negative. It integrates to 1 over the entire R2. And now I can take any event. It doesn't have to be the intersection of two marginal events. It's an arbitrary event. And the probability that the pair, the randomly drawn pair, is in A, is now the double integral over A.
And when they're independent, that integral.
Then things simplify. If I can write, if I have a set of this form, which I can write as A cross B, and if they're independent, then yes, I can reduce it to the integral over A times integral cross B. But in general, no. In general, it just gives me some arbitrary integral over some set. Any other questions? All right, then let's start. We're going to start talking about lecture notes 2. So what we're going to do here is talk about probability inequalities. The probability that x is bigger than something is bounded by something. Why do we care about that? Well, there's lots of reasons why we care about it. Sometimes these probability bounds are useful in and of themselves. So this will turn out to be true in a lot of statistical and machine learning problems. We want to bound the probability that we misclassify something and that we'll lose these bounds. In particular, we're going to get to something called Hoeffding's inequality, which is a central inequality that you're going to see for the rest of your careers all over the place. So it's very, very fundamental. And, but also it's a stepping stone, because we're going to talk about something called BC theory, which is sort of a more advanced version of probability bounds, which gets used a lot. And then from there, we're going to go into what's called convergence theory. Convergence theory talks about what happens to statistics like x bar as I get more and more data. And the whole point of collecting data is you want to get a lot of it. And so when you get more and more data, you want to ask what's happening to my random variables. That's convergence theory. But to do convergence theory, you first have to do probability bounds, because they play an important role for the developing of theory. So probability bounds are going to be underlying a lot of the stuff that we do. And so let's start talking about some of these bounds. There's really only 2 or 3 main bounds. I mean, you can find books filled with hundreds of these bounds, but the truth is, there's really a couple of main ones. Markov's inequality, which maybe you've seen before. Hoeffding's inequality, which some of you may have seen before, but I won't assume you've seen it before. And the Gaussian inequality. And those 3 are probably the most important. That'll get you through life pretty well. We just know those 3 inequalities. So I won't do every possible inequality in the world, but we'll do these really important ones. And let's start with the Gaussian tail inequality. So this selection of 281. So we're going to take a standard normal random variable. It looks like this. The thing that's really special about normals, and of course it's symmetric and has a nice formula and so on, but it's that the tails of the normal die off very quickly. That's what drives all of these probability bounds is how fast do the tails of the random variable die off. And so that allows us to say that the probability that the absolute value of x is bigger than epsilon, so in other words, actually, you know what, I don't like calling it epsilon, because epsilon implies some sort of small number. Let's just think of an arbitrary, it doesn't matter whether we call it epsilon or t, but I don't want to give you the impression I'm talking about a small number. Just an arbitrary positive real number t, so here. So the probability we're talking about is this tail, because of the absolute value. And the idea, of course, is that when t gets big, this probability should get small. And in fact, it gets small very quickly. The inequality is that it's e minus t squared over 2 over t. The important part is this e, right? This goes to 0 very quickly as t gets big. Don't make it up to just better. And this is sort of the best possible thing you can hope for. That probability is going to 0 very quickly. And we can also apply this, well, now if I have n observations for normal, and I can say the probability that x bar, the sample mean, is bigger than t, then is less than or equal to 2 over root n t e to the minus n t squared over 2. And for n large enough, this is less than 1. So I'll write for n large, I can get rid of that and just concentrate on this part. So what is this saying? It's saying that x bar, the probability x bar is bigger than t, is going to 0 very quickly. It's going, in terms of t, look how fast that goes to 0, but also in terms of the sample size n. Then it gets bigger. This is going to 0 exponentially quickly. It's very unlikely for x bar to be very far from 0. And so let's prove this. And a lot of the other inequalities that people derive are trying to mimic the Gaussian tail inequality, but for non-Gaussian distributions. In fact, that's what Hoeffding's inequality is sort of trying to get a more general inequality that behaves like that, but without the Gaussian distribution. Okay, so let's just prove this. I'll do the proof for single x. The proof for x bar is pretty straightforward because we know x bar is also normal. That's all. I won't do that case. And the other thing is that, to do this probability inequality, all I have to do is do this one, and by symmetry, this one's the same. That's where the 2 comes from. So I'll just do one side, and then the other side comes by symmetry. So what's the probability then that x is bigger than t? That's the integral from t to infinity. And this is a common thing I'll do in this class is that I often use phi standard normal density, so that's. And what we're going to do is multiply and divide by s. Doesn't change anything. But this one, the biggest is when it's at the beginning, t. So this is less than or equal to, pull this out and say 1 over t. S is always, in this range, S is always bigger than t, so 1 over S is always less than or equal to 1 over t. So I pulled this out and made it bigger. And now I have this. Now one thing you can check here is that a good property to remember about normals is that phi prime of S is minus S phi of S. Check. So that means S phi of S is actually minus, this is actually minus phi prime. So this is minus 1 over t to infinity. And, well now, the integral of the derivative is just a function. So this is phi prime at infinity, which is 0, minus p prime of t, there's a minus there, so this is just p t, which is exactly the stated inequality. So it just comes from elementary properties of how the normal density function behaves. Integration by parts. So that's nice. This is a good thing to know, but it really is restrictive. That proof really used the fact that it was a normal density. So now our goal is to work towards Swift's inequality, which is going to give us a similar inequality about averages without the Gaussian assumption. And the starting place is a very simple inequality, probably seen, which is Markov's inequality. Markov's inequality. Markov's inequality by itself is a very, very weak inequality, but it's still important because it's often used to prove other inequalities. So Wolfing's inequality relies on Markov's inequality. So we really need Markov's inequality, which says that suppose that we have a random variable for this inequality, we're going to assume that the random variable is bigger than or equal to 0. And then we're going to say, well, what's the probability that x is bigger than t? Markov's inequality says it's less than or equal to the mean of x over t. So there's an implicit assumption here, which is that the mean exists. The mean isn't well defined. The tails are too thick, in other words. And this inequality doesn't mean anything. So we're assuming that it has a mean, finite mean. It's an example of a distribution, by the way, that doesn't have a mean. Cauchy. The Cauchy distribution, which looks like there's some constant, which I won't remember, but then it's something like 1 over 1 plus x squared. You know, it looks just like a normal. It's pretty hard to tell the difference. The difference is that the tails die off very slowly. And if you go to your, whatever your favorite program is, if you're in CS, it's MATLAB. If you're in statistics, it's R, but everybody should use R. MATLAB sucks. Switch to R. And so you go to R and you take a random sample of Cauchy's, and look at how it behaves. I mean, it's really interesting. Because of the thick tails, you get these extreme observations every now and then. You get these outliers. And it doesn't have a mean. If you try to integrate this, the mean isn't well defined, and that's because, again, of the thick tails. So all these probability bounds are going to assume that we're not dealing with a thick tail distribution. So Markov's inequality in particular is assuming that the mean is a well-defined one. So let's prove this. The proof is one line. What's the mean of x? Well, the mean of x, by definition, is the integral of x times e of x. But since this is a non-negative random variable, I only have to integrate from 0 up to infinity. And let's see. So now I'm going to say, well, instead of doing the whole integral, I'm only going to integrate from t to infinity. everything here is non-negative, right? This is non-negative, non-negative, so I'm summing up a bunch of non-negative stuff. If I make it smaller, then I'm not integrating as much stuff. So the inequality can only get smaller. And x is always bigger than or equal to t, so this is bigger than or equal to t, so that's bigger than or equal to t times t of x. Which is t times the probability that x is bigger than t, and we're done, because that says that the probability that x is bigger than t is less than or equal to the mean of x. So that's very simple, but very useful. In fact, the first use of it, what we want to sort of do now is, the game is to kind of amplify Markov's inequality. Actually, let me first of all say, why is it, do I say it's a weak inequality? Well, as t gets bigger, how does this probability decrease? It decreases like 1 over t, which is pretty slow. Compare that to the Gaussian inequality that I just erased, which was that it was going down like e to the minus t squared. It's going down very quickly with t. So that's what I mean when I say this is weak inequality. It goes down very slowly. And so the game is to kind of amplify Markov's inequalities and some tricks. The first one, this is another one you've probably seen before, is Chebyshev's inequality, which is spelled differently in every textbook. It's a Russian name, and how do you transliterate it into English? I don't know one way to do it. That's how I'm doing it. Which says, what's the probability that x minus its mean is bigger than t? But we want to take advantage, and here's always the game. So, first of all, I'm already telling you it has a mean, but suppose I also tell you this random variable has a variance. Somehow the fact that the variance exists is giving you more information, and you want to find a way to use that information in your inequality. So the natural thing to do here is, since variances involve square things, is let's square both sides. That's the probability. And now I can use Markov's inequality. Markov's inequality applies to any non-negative random variable. That's a non-negative random variable. And it says it's less than or equal to the expected value of this divided by this. But of course, this is the definition of the variance. So the cool thing is that this goes to 0 faster. 1 over t squared instead of 1 over t. We really only used Markov's inequality, but the trick of squaring everything allowed me to bring the variance into the picture. It was the squaring it, but I couldn't have done that unless the variance existed. So this is the game, is by using more information like the fact that the variance exists, I can leverage Markov's inequality, but by applying it at just the right time, and here the right time is after squaring things, I get a sharper inequality. Okay, so Hoeffding's inequality is going to be the extreme version of this. Actually, I'm going to jump ahead and state the inequality, then we'll come back to proving it. So what Hoeffding's inequality says is the following. Suppose I have n IID random variables. Remember, always assume IID unless I say otherwise. And let's suppose that let's let mu be the mean. Now we need an extra assumption to get a sharper inequality. I don't want to assume that it's Gaussian. I want this to be more general than that. And the key assumption in Hoeffding's inequality is boundedness. Suppose that these are bounded random variables between two numbers, say a and b. Now, bounded tells us that the tails are very thin. You can't get thinner tails than that, right? It's saying outside the interval AB, there's no probability. So this is definitely, there should be some lots of information there for us. That the probability mass is 0 outside this interval. The tails can't be any thinner than 0. So that should be helping us. We should be able to get something out of the Gaussian inequality. And in fact, here's the inequality. The probability of x bar minus mu, how far is x bar? So this is how far is the sample mean from the true mean. And we're hoping that's not too far away. Probability that's bigger than t to the minus 2n t squared over d minus a squared. So that's looking a lot like the Gaussian inequality. That's an exponential inequality. It's a significant improvement over Markov and Chebyshev. So this was proved by Vasily Hufting in 1963, I think. It's had a huge impact on statistics and machine learning. It's going to be the basis for a lot of things we do. So I think it's worth going for the proof because it's such a fundamental inequality, and if you've never seen the proof before, it's pretty slick, cool proof, and it shows not just, the important thing about this proof is it's not just showing you how to prove this theorem, but the tricks that get used here get used a lot. So you're learning some good tricks to proving other things if you know how to prove Hufting's inequality. So let's see how much we have, 5 minutes left. So let's back up. Stop in the middle. So here's what I'm going to do. There's 2 tricks, basically, using Hufting's inequality. And again, I call them tricks because they are ideas that you can use for proving other things. The first one, which we'll go over in detail on Friday, because I don't want to start it now and get interrupted, is going to be the fact that because this is the boundary random variable, its moment generating function, all its moments exist, and hence its moment generating function exists. And we're going to try to somehow leverage that fact. Remember how we leveraged the variance in Chebyshev inequality? We said the fact that the variance exists should somehow be useful. Well, the fact that the moment generating function exists should somehow be useful. So we're going to use that fact. And then we're also going to do another thing, which is how do we bound the moment generating function? I don't want to have to compute the moment generating function for every different distribution. I want to use the fact that this is a boundary random variable. I should be able to get some sort of universal bound on its moment generating function. Those are the 2 tricks we're going to use. Let me show you the leveraging trick. So that's shorter. Then we'll come back to bounding the moment generating function. And this is sometimes called Chernoff's method or Chernoff's trick or something like that. Herman Chernoff, statistician, Harvard. And the idea is this. If I want to say, what's the probability that x is bigger than t? Here's a general fact. This is less than or equal to. This is the infimum. If you're not familiar with infimum, just think of it as a minimum. So the minimum over all t's greater than 0 of the following quantity. E to the minus, oh boy. Okay, I'm switching back to epsilon. There's always a danger of departing from the notation you mentioned of notes. I should just stick to my notation. Because I would have ended up with 2 different t's here, which would have been pretty confusing. Okay, so this is back to epsilon. Probably x is bigger than epsilon is the infimum over t. This is an extra parameter we've introduced called a variational parameter, something we get to optimize over. And this is e to the minus t epsilon times the moment generating function. So let's think through what we have here. Remember, this is just the definition of the moment generating function. So that's a function of t. And this is another function of t. And so we'll get an expression here which is a function of t. And now we get to minimize this over all possible t's, and that gives us an upper bound on its probability. And notice that we are bringing into it the moment generating function. Okay, a very clever idea, and the proof is very, very simple. All we do is say the probability that x is bigger than epsilon. We're going to do the same thing. If I want to bring the moment generating function into this, well, the moment generating function involves the exponential function. So let's just, all I'm going to do is take the exponential, both sides, and in fact, we're going to raise both sides to the power t. That doesn't change anything. So I haven't done anything. It's just like Chebyshev. I just squared things here. I'm just taking e. And t here is an arbitrary positive number. This is true for any arbitrary positive. Now I just apply Markov. Markov says the probability that this random variable is bigger than this is less than the expected value of this times 1 over this. So that's exactly this. This is e. And where did the minimum come from? The minimum comes from the fact that this is true. This inequality, starting here, this is less than or equal to this, but t was arbitrary. This is true for any t. I didn't have any particular t there. Since this is true for any t, it's also true if I take the minimum of the t, which is where we get that. So what we're going to do on Friday is we're going to use this Chernoff trick here, and we're going to end up with the moment generating function of x bar. And then the one that takes a little bit more work is to try to get the moment generating function of x bar using this fact that it's bounded. Can we get some sort of nice bound on the moment generating function? And we'll use a few tricks involving convexity and things like that. So, any questions before we break? You don't, I'll tell you the rule, but if you don't ask questions, that means I'm going way too slow, so I'll double the speed next time. All right, see you Friday.